So this will be our first asynchronous online session, and you should have this video. You should be able to get this video from your e-learning classroom. Instead of doing the usually more common approach of writing the equations step by step, instead of doing that, I'm going to walk you through the derivation of diesel cycle efficiency by using complete notes of mine. But the idea here is the same, except that I'm going to make the video as short as possible by writing the equations and the step first, as in our screen now, and walk you through the explanation. And this explanation will be a bit different from those in our notes. I believe it's from page 23. It'll be a bit different from that, but the idea here remains the same. So let's go through the diesel cycle. First off, you should be able to notice the cycle, the PV diagram. So the difference of diesel cycle, the difference between diesel cycle and Otto cycle is that the heat addition process, which is the process of 2 to 3 heat addition, is a constant pressure process, or a constant pressure step. So that is why the heat addition here will give you a flat line for the pressure, and the heat removal step or process is the same as in Otto cycle. And next, if you look at the TS diagram, in practice, in the real example or in the real process, the graph should be about the same, but with a little bit difference in the curve, because the heat addition process is of a constant pressure, so you'll have a little bit different curve from the Otto cycle. So it should be a different curve, okay, compared to the Otto cycle, but it should be that much different. So if you were given this type of questions for your test, I won't be too critical in judging the way you draw the curve. Okay, you may make the curve a little bit curvy, it's okay, or a little bit straight line is still okay with me. Now let's look at the process. For process 1 to 2, the isentropic compression, so you have the relation of T1 and V1, which is volume 1 and temperature at 1, and T2 and volume 2, V2, which is the temperature and pressure at the temperature and volume at point number 2. Now the idea here is exactly the same. We are trying to do exactly the same process, the same step as the way we derive the Otto cycle efficiency by using compression ratio. So the logical step here is to find the ratio of the temperature and its function in volume. So instead of having to calculate our efficiencies from temperature, we want to be able to calculate them from the volume. So you need to put the relationship of temperature and volume. So here's the idea. Okay, find relation between temperature and volume. So here we have our first expression of the ratio of T2 over T1, where it's just actually equivalent to the compression ratio powered by K minus 1. Now the next step is for process 2 to 3, and if you refer back to the PV diagram, so this is the process of heat addition, okay, and it is in the form of constant pressure. So from the state equation, you have the pressure to be constant, and if you manipulate the state equation, so this is the state equation, if you manipulate the equation from the fact that pressure is constant in this case, you can get to the conclusion of T over V is a constant. Hence you have T2 over V2 is equals to T3 over V3, and V3 over V2 is a ratio that we can define as the cutoff ratio. Okay, the term used here is I try to be as consistent as possible with the terms used in the textbook, so I'm using the R subscript C here, RC here, as the cutoff ratio. So we have from the process of 2 to 3, we have our definition of temperature 3 over T2, temperature 2, to be equals to the cutoff ratio, which is volume 3 over volume 2. The next step is, again, we have an isentropic expansion. So in the case of isentropic expansion, we have T4 multiplied by V4 power to K minus 1 equals to T3 multiply V3 power K minus 1. And in this case, we know that volume 4 is equals to volume 1, and from our cutoff ratio, we know that volume 3 is equal to the cutoff ratio multiplied by volume 2. So we get T4 V1 power K minus 1 equals to T3 multiplied by RC V2 in a parenthesis powered by K minus 1. And with a little algebraic manipulation, we can get to our equation 3. Now, by definition, for any gas cycle, the efficiency is 1 minus Q out, which is the remove heat over the added heat. So this is the definition of any gas cycle efficiency. And if we go back to our TS diagram, we can see that our highest temperature is T3, and the cycle, the process of heat addition is from the process of 2 to 3. So we have our heat addition to be Cp, because of constant pressure, multiplied by T3 minus T2. For our heat removal, the process is of constant volume, so we have Cv multiplied by T4 minus T1. So this is our for heat removal, and this is for our input heat. And if we again do the algebraic manipulation, we can get to this equation. And remember that Cp over Cv is equal to K. Hence, if Cv divided by Cp, we have the inverse, which is 1 over K. And we may substitute Cv over Cp to our efficiency definition. Now, this is where the tricky parts begins for diesel equation, because we don't have a nice multiplier to begin with, but we do have our compression ratio and our cutoff ratio, RC. So this is our compression ratio. And this is our cutoff ratio. So the best way to attack this type of problems is to turn everything into the ratio so that we can convert it to the volume ratio instead. So this part, T4 minus T1 over T3 minus T2, we can rewrite them to be in the form of ratio of T4 over T1 and T3 over T2 and also T1 over T2, which is luckily a very convenient form of ratios, okay, especially T1 over V2, where we have the ratio already calculated for us from equation 1. And T3 over T2 is also calculated from our equation number 2, which is the cutoff ratio. So we are only left with the challenge of finding the ratio of T4 over T1. And this can be done directly by taking all the ratios together, all the ratios, and trying to, and by substituting and manipulating, which is basically algebra here in this case. So you can first calculate the ratio of 3 over 4 from the first, from 3 over 4 here. So this is for 3 over 4. And from the cutoff ratio, we can know the values of T2. So we may replace T3 with RC, the cutoff ratio, multiplied by T2. And this will give us our definition of T2 over T4, which can then be conveniently calculated by multiplying T2 over T4 with T1 over T2 to give us a T1 over T4 ratio. So this is our T1 over T4 ratio. Of course, it is actually the inverse of the ratio that we wanted, that is T4 over T1. So if you take the inverse, then you'll get the T4 over T1. And substituting every ratio into T4 minus T1 and T3 minus T2. So you have the equation written completely in the form of compression and cutoff ratio. And substituting everything back into the original efficiency definition, you'll get the final equation of 1 minus 1 over k multiplied by 1 over r power k minus 1 multiplied by rc power to k minus 1 over rc minus 1, which may be a little bit different from the one that you have in the textbook or in the page, in our slides, page 23, where in page 23, the slides, you have the equation is laid down to you by 1 minus r1 over rk minus 1 rc power k minus 1 over k rc minus 1. Now these two are the same equation, okay? It's just that I prefer to write everything in a separate form for clarity. Now here comes the homework. Okay, the homework is prove that for the same compression ratio R and a constant value of RC, the efficiency of let's get it right. Okay, the efficiency of Otto cycle is larger than diesel cycle. So this is the homework that I'll be expecting for you to complete the coming Friday. And let's use the value of K to be 1/4, and RC is a constant, but if you feel the need to use any number, I'm going to set RC to be equals to, let's see the graph, let's see the diagram first. RC to be equals to 1/4. Let's go 1/4. RC to be equals to 1/4 of the compression ratio. So this is the homework I'll be expecting to collect from you this Friday.